So, Bomshir, how are you? Huh? I hope you didn't have a good sleep tonight and you enjoyed something in Sao Paulo. It's a beautiful city. We had plenty of fun. We arrived this morning 4 a.m. So in case that I have some interruptions, please be patient with me. We start this morning with network and architecture. And our first presenter is coming from BMW. It's Germán Ferreira. He is part of the IBM team at BMW, where he is responsible for prototyping platform on 10BASE-T1S for testing and validation. And currently he's also coordinating its effort on diagnosis of IEP, DoIP. And he is graduated in Spain at the Universidad Pontificia de Comillas. So, Germán, please join us. The floor is yours.
Yep. Thank you for the introduction. So, hello everyone. My name is Germán Ferreira, and together with my predecessor, Gumersindo Veloso, we prepared this presentation. So today we are not going to talk about the typical topic of the IEEE event. Today we're going to talk about the vehicle diagnostic communication and especially the DoIP protocol and its optimization for zonal architectures. So for today, we're going to first go back in time to the history, to review the history of vehicle diagnostic communication. Then I will go to the details of the ISO 13400, which is the standard that holds the DoIP protocol. Then I will explain you the basics of the protocol for those of you who are not that familiar with it. And then I will show you the limitations that we at BMW found in the protocol for our current EE architectures and in the future. So first, let's go back in history. So the first efforts to initiate the vehicle diagnostic standardization started in 1979 when the Society of Automotive Engineers started to recommend some physical connectors and signal standardization for engine use cases. Those efforts were then crystallized in 1991 with the introduction of OBD1 in the state of California, and 6 years later it was extended to the whole United States. In Europe, we adopted the EOBD for our petrol and diesel cars in 2001 and 2003. And then, well, OBD2 over CAN was extended. And then in 2012 occurred a major change. The first release of the DoIP came, and it was the vehicle diagnostic communication over Ethernet, which was based also in the HSFZ protocol of BMW. And then in 2019, the current release of DoIP was released. And now, at the end of this year, we are expecting the newest release of the protocol. So always in those standardization efforts, the vehicle diagnostic communication was ahead of the EE architecture of the time. So is this still the case? Are we still ahead? That's what we're going to review in this presentation. So today we have DoIP, which is basically a transport protocol, meaning to operate with UDS and ODX. As I mentioned before, it was standardized in the ISO 13400. And the software specification for embedded systems is already available in the AUTOSAR consortium. Also, the scope of the protocol is not just limited to a single vehicle, but it's meant to operate in a network of vehicles. And it not just considers all DoIP entities in the vehicle. It is also considering some legacy communication systems as CAN or FlexRay, and therefore vehicle gateways are considered in the protocol. And in the current release, we have some really interesting features. For example, we have the optional use of secure communication channel using the TLS, and also the use case of internal testers is considered. Internal testers are, for example, on-the-air updaters. And those testers need also to behave with the same rules as the external clients, the ones that you will connect over your OBD port. So now let's focus on the hardware architecture. So in the slide, you can see the hardware architecture approach of the ISO. I will guide you through the slide. So you can find on the bottom part of the slide the external network, and here on the upper part the in-vehicle network of a single vehicle. So the external network is composed of client or clients, which it could be, for example, your tester at the vehicle repair shop. You could also find additional vehicles, as I mentioned before. And also you can find some other network nodes, which it could be, for example, just computers, terminals. Then in the vehicle network, we can find some of these elements. So we can find, for example, the edge node, which is basically your separating point between your external network and your internal network, which it could be basically where you connect your OVD cable. Then you will find a DoIP gateway or gateways, which are going to connect your Ethernet with other communication systems, for example, CAN or FlexRay. You will also find some client, for example, for the on-the-air updates that I mentioned before. Some other nodes which might not have a DoIP implementation, might not just be diagnostifiable, and well, other DoIP ECUs. So what we found out when we were working on the protocol with other OEMs to enhance it is that the protocol is implemented differently across the OEMs. What I mean by this? So there are different approaches by the other OEMs. For example, some of them think, well, the DoIP communication is just going through the external network and it's ending on the OVD connector. Others are designing the network so that all the communication must go through the edge node, through the gateway, including the on-the-air testers. And for some others, well, they just think that not all DoIP rules are necessary in the vehicle network. And all of these approaches are fine as long as you're complying with the current legislation. However, we at BMW would like to remark that the DoIP protocol is already considering those internal and external connection use cases. And we think that it has some advantages, and I will guide you through this. So here in this slide, this represented a reduced implementation of the DoIP protocol, in which the tester must always go through the vehicle gateway to flash the ECUs. Now you will see the architecture, instead of being vertically presented, it's now horizontally. So you will find at the left side the external network, which is now reduced to just external tester. And on the right side, you will find the ECU to perform this flashing scenario, and also an internal tester. So now, because the ECU doesn't have a DoIP implementation, the vehicle gateway needs to have the following software elements. It needs to have the DoIP server to connect with the client, some routing code, and what is called in the slide an Ethernet diagnostic handler. With this software constellation, now it's not possible to access from the server ECU directly from the client, and we have to go mandatory through the gateway. So this software architecture is restraining our communication workflows, and moreover, because we will need 2 TCP connections from the external tester to the ECU, we are also limiting our flashing performance. Now let's check if we take the full DoIP approach. Now we come to the following picture. The changes are basically that the ECU is now a pure DoIP server, and now the DoIP gateway is providing also a DoIP server instance, some routing code, and a DoIP client. And now you can decide what is your communication workflow for your diagnostics or flashing scenarios. You have the flexibility to do this. And moreover, you also have an uniformity in your software, because now you just have to design, develop, and maintain 3 software units compared to the 5 that I explained before. Now let's go to a simple DoIP scenario for those of you who are not that familiar with the protocol. Now let's imagine that we are bringing our 3 series to the workshop, just for a simple vehicle inspection. Let's suppose that we connect a tester, and the tester is in another subnet than our vehicle network. for example, the ECU 1 and 2. And we just want to perform a simple diagnostic to the ECU 1. So we will connect our tester to the OBD port, and then the tester will have to open a TCP connection against the gateway and perform a so-called routing activation. A routing activation is, in the end, like a functional session handling in which the ECU can accept a tester or neglect it. So once this is done and is accepted, the gateway will have also to open a TCP connection to the ECU1 and perform a routing activation. When the ECU1 accepts this, then the tester can start to send the diagnostic request. So let's make this scenario a little bit more complex. Let's go now to the production plant. Now, in the production plant, we have multiple testers. And this is actually a scenario that we are doing at BMW. As an example for this presentation, we can imagine that the tester number 1 is just the supervisor of the whole process. The tester number 2 is a tester who is in charge of flashing a particular ECU. And the tester number 3 is just configuring some ECUs or configuring some sensors or actuators. So now, what's the situation here? Additional testers will need to open their own TCP connection against the gateway and perform their routing activation. And moreover, the gateway will need to do the same against the ECU. So it will have to also open a TCP connection and perform the routing activation. And you might think, okay, so what is the problem of this? Let's escalate the situation. Let's imagine that in our network we have 3 testers connected at the same time and we have 15 Ethernet ECUs. With this architecture, we will come up with 48 TCP connections that the gateway needs to handle. And this requires, of course, resources. For each TCP socket, we will need at least 6 kilobytes of RAM per socket, and even more if we want the receive window of the TCP to be more performant. On this DoIP server side, so on our target ECU, this will cause more receive interrupts on the software, and we will observe on the network some header traffic that is not adding any value to the communication. So therefore, we are adding cost, inefficiency, and complexity to our vehicle diagnostic system. Is this possible to optimize? Well, we can optimize this behavior if we allow the multiplexing of the TCP connections, so that you could take a socket and you could share it through more than one tester. How this will work in the ISO? So here, this is the proposal from the BMW side to allow the multiplexing of testers. So in the 2000, here on the left side of the screen, you will see the connection table modeling of the current ISO specification, and on the right side, you will see the proposal from the BMW side. I will explain this a little bit for those of you who are sitting at the back and cannot see the slide properly. So the connection table is basically the model that is relating the testers and the socket connections. And all of this is performed through the routing activation mechanism. So in the current modeling of the ISO, we have a so-called socket handle in that modeling object, source address, and a so-called connection state, which is registering the socket status and the DoIP connection status. Then we also have so-called initial and general inactivity timers, which are mechanisms to handle the sockets for the disconnection point of view. And then we have some optional information related to the tester, which is called the authentication and confirmation information. So what we designed at BMW was, okay, let's take the properties related to the tester and move it to a separate modeling object, which we called the DoIP client entry. Now this object doesn't have the constraint to have a one-to-one relationship, but we can decide to have one-to-n. So we can have a custom multiplicity. In this new object, we will have the source address of the tester that we have seen in the previous modeling. We will have an additional connection status to have a relationship between the socket status and the DoIP entity status, and also those optional information that we've seen before related to the tester, the confirmation and authentication information. Because the timers are really related to the socket, we left them there under the main object. So what's the advantage of this model? We are still providing mechanism for the ECU to protect because we are still using the routing activation. We are still providing the flexibility to allow the multiplexing of sockets. And if for some reason you want to be backwards compatible, you can do this. Just limit the multiplicity of this element through configuration to 1. And that's it. Now, we have seen along the course of this presentation that the DoIP protocol is serving the purposes of our current EE architectures. So for example, we can bring our car to the workshop and we could let it perform diagnostics through an OBD tool. And also we are allowing to perform on-the-air updates. So what is now the next step? Well, if we fully implement DoIP, the protocol also is going to suit our future zonal architectures. Let's imagine the following situation and the future possibilities. Now we took our 3 series and we enhanced its vehicle architecture. We will have a zonal at the front of the car, which is depicted in the picture as gateway 1, and we will have another zone at the back of the car, which is depicted as gateway 2. This brings us the possibility, for example, to have not just one OBD connector, but to have 2. And then we could, for example, flash faster. We could, for example, take one OBD tool and flash one zone and take the other point of the vehicle and flash another zone of the vehicle. Also, because the number of Ethernet ECUs are going to be increased in the future, the multiplexing of TCP testers is also going to optimize those zone controllers that we see here. And moreover, now there is another situation that is coming in. Let's take, for example, the ECU1. The ECU1 can be now accessed from 2 points. It can be accessed from the gateway 1 and the gateway 2. So we will need a measure protection mechanism for this. Well, actually, we don't need it. We already have it. It's routing activation. We are maintaining this in our concept. And now if, for example, you misconfigure a flash sequence and you want to perform the flashing on the ECU3 from both of your tools, that could be protected with the routing activation mechanism. So now with this slide, it will bring me to the conclusions. So we have seen that having more than one access point to the vehicle has several advantages. For example, on the flashing use cases, we have seen that the DoIP protocol is already providing the mechanisms to manage the complexity of the EE architectures. But also we have seen that we can improve the DoIP protocol, for example, by adopting the multiplexing of testers. So I would like to thank you all for your attention and also hoping for you to support us for this concept. Thank you so much.
So Germán, thank you very much. Are there some questions?
All right.
Seeing not so much. So you mentioned also that there are some interpretations of the standards. How to avoid those in the future?
We will need, I guess, to work even closely in the standardization organizations.
Okay, standardization is the key.
Yes.
All right. Any further question? One is coming up.
Hi, Eric Parra here, Technique Engineering. You're mentioning that the DoIP implementation that you're proposing has to do with the structure on the gateway. I have a different question here. What about the physical layer interfaces on the OBD? Is there any guidance into, will it remain being 100 base TX with an activation port which is needed because the PHY is not EMC compatible? Or are there like more official approaches into integrating, like Thomas Koenigsegger proposed 2 years ago in the Automotive Ethernet Congress, 1000 base T1 directly on the connector? Is this part of the scope that you're looking at?
Yeah, that's an interesting point. Actually, the physical connection is guided into a different standard related to this one. Here we are just focusing on the functional part of the protocol, on the DoIP. But for example, that will help actually a lot if we want to flash even more data faster. Because that could be that with your current physical layer, you are running onto a bottleneck for your data in the production plant use case, for example.
Okay, pretty cool. Thank you.
So any further question? So then thank you again.
Yep. Thanks a lot.
So our next presenter is Siddharth Sukla. Siddharth works as a senior product manager for intrusion detection and prevention solution at ETAS. ETAS is a Robert Bosch company. He has been associated with ETAS for over 7 years now. He worked in many different places in Japan, Sweden, Germany, India. Impressive. Siddharth received his bachelor's in electronics and communication engineering, master's in embedded systems, and a PhD of electrical engineering with focus on security and low power wireless sensor networks. Probably I have something in common with him. Siddharth, where are you? Okay.